All right, let's dive in. Today, we're cracking the code on something that happens all around us, every single second. Chemical reactions. I mean, from the toast you make in the morning to the very air you're breathing right now, chemistry is basically writing the story of our world. And today, we're going to learn how to read it.
So let's start with a really simple mystery from the kitchen. You can take an ice cube, melt it into water, and then freeze it right back into an ice cube. No problem. But have you ever tried to uncook an egg? Yeah, you can't do it. So why not? Well, the answer comes down to a huge difference between a change that's just temporary and one that's permanent.
And, spotting that difference is our very first mission. Think of us as chemical detectives. We're about to learn the clues to look for, the telltale signs that something totally new has been created, something that you can't just easily switch back.
Okay, so here's the absolute key difference. A physical change, like ice melting, is just a change in form. It's still H2O, right? It just went from solid to liquid. But a chemical change, like cooking that egg, permanently scrambles the very makeup of the matter. The proteins inside the egg have been totally transformed into something new.
And the official name for that permanent transformation is a chemical reaction. So what's actually going on? Well, it's a process where the bonds holding atoms together literally break apart, and then the atoms rearrange to form brand new bonds, creating completely new stuff. This is the engine of change in the entire universe.
Now, to keep track of all these incredible changes, chemists came up with a kind of secret code, a special language to write down exactly what's happening. We call them chemical equations, but really, you can just think of them as the recipes of reality.
And just like any recipe, you've got two basic parts. First, you have your reactants. Those are your ingredients, what you start with. Then, after the reaction happens, you get your products. That's the final dish, the brand new substance you've just cooked up.
So, for example, when you burn a piece of coal, your reactants are the carbon from the coal and the oxygen from the air. They react together, and the product is a totally new substance, carbon dioxide gas. Super straightforward recipe, right? But there's one fundamental rule that governs every single reaction. And this is it, the law of conservation of mass. What this really means, in simple terms, is that you can't just create or destroy atoms out of thin air in a chemical reaction. Nope, you can only rearrange them. Everything you start with has to be accounted for in the end. It's like the ultimate balancing act.
Check this out. In this reaction right here, just look at the table. You see how every single atom is accounted for? The number of silver atoms, Ag, before the reaction is the same as it is after. Same for sodium, Na. Same for everything else. Nothing gets lost. This is what we call a balanced equation. It's a perfect accounting of every single atom.
Okay, so now that we know how to read the code, let's meet the main players. It turns out that most reactions fall into one of four main categories. Think of them as the usual suspects that show up again and again. Let's do a quick profile on each one.
First up, we have the combination reaction. This is exactly what it sounds like. Two or more things just combine to form one single, more complex thing.
A plus B comes together to make AB. Simple as that.
Next is the total opposite, a decomposition reaction. This is where one big complex thing breaks down into simpler little pieces.
So AB breaks apart into A times B. One thing becomes many.
Third, we've got displacement. This one's kind of like a dance-off. A more reactive element comes along and literally bumps a less reactive one out of its spot in a compound. It's all about who's got the better moves, chemically speaking.
You can see it here. A swoops in, kicks B out, and partners up with C, leaving B all by itself.
And finally, double displacement. Now, this isn't just one element getting bumped. Oh no, this is a full-on partner swap, where two compounds completely trade dance partners. See? A and C totally switch places. It's a complete exchange, and boom, you've got two entirely new compounds. So, we've got our types of reactions, but here's the next really cool layer. Not all reactions happen at the same speed. I mean, an explosion is basically instant, but rust can take years to form. And the best part is, we can actually control that speed. So let's look at how we can hit the accelerator or slam on the brakes.
Turns out there are quite a few dials we can turn to control how fast a reaction goes. By changing things like the temperature, or how concentrated the ingredients are, or even the size of the particles, we can get really precise control over how quickly new stuff gets made.
Let's just take particle size for a second. If you drop a solid piece of tile into acid, yeah, it'll react, but slowly. But what if you crush that same tile into a fine powder? It reacts way, way faster. Why? Because you've created a massive amount of surface area for the acid to attack all at once. Smaller particles just mean a faster reaction.
And what about this last one? A catalyst. A catalyst is like a chemical matchmaker. It's a substance that helps speed up a reaction by helping the reactants get together more easily. But, and this is the cool part, it doesn't actually get used up in the process. The enzymes in your stomach that digest your food, they're catalysts. They speed up reactions by millions of times. It's amazing.
Okay, so we've learned the secret code, we've met the main players, and we've even figured out how to control the speed. Now let's bring it all back home and see how this stuff explains the chemistry you see every single day.
Remember rust? That reddish-brown stuff you see on an old bike or an iron gate? Well, that's corrosion, and it's really just a super slow-motion oxidation reaction. It's the iron reacting with oxygen and water in the air to form a brand new compound, iron oxide.
Or how about when you leave some cooking oil out for too long and it starts to smell funky? That's called rancidity, and it's the exact same idea. The fats and oils are reacting with the oxygen in the air. They're oxidizing and creating new molecules that have that awful smell and taste. It's chemistry you can actually smell. So from an apple turning brown on the counter to the fizz you see when you mix baking soda and vinegar, chemical reactions are happening everywhere all the time. But now you know the code. You know how to read the recipes of reality. So the only question left is, what new reactions are you going to spot today?